research that I'm doing now. This is from a few months ago. And that concerns precursors for aerosol cystic chemical deposition of metal sulfides. In short, what I've been doing is designing chemicals like this that would readily decompose to form functional thin. But why do I want to do this? So metal sulfides fall into a class of material called metal dicarbonate. And this consists of a metal atom with two chalcogen anions. So chalcogens are sulfur or selenium or tellurium. I don't know if anyone has any experience with these, but they stick. On a good day, I go home and fully late. But these materials are really interesting because they can have very interesting electrical properties, which mostly they can be semiconductors. And as such, they can use a variety of applications in things like electronics. So couple this with the fact that they can have 2D solid structures. You can potentially have this situation where we have future electronic devices which are really small scale. When I say full scale, I'm talking kind of nanometer sort of scale, and we can get kind of below that for which is a simple electronic component. But in order to realize these materials in next generation electronic devices, we need to find a scalable and controlled technique by which we can follow them, because of the interesting in their architecture. So aerosol chemical availability is a viable technique to do this. It's quite a really nice technique that's relatively simple. You have a pot precursor, which you aerosolize, get the interface phase, which is into a reaction chamber where it can decompose polymers. All very good. The whole act of aerosolizing into the gas phase means to be circumventing the volatile precursors, which is conventional CVD. Having said that, you still need to adhere to criteria for your precursor, and that's what we there.
Can you just stand back a bit? I need you to pick up on that microphone. Didn't share screen. Actually, what I need to do.
Yes. Okay. So I'm looking at the precursor design. Precursor design has a really big impact on the nature of the deposition that you manage to achieve. So despite the fact that it doesn't need to be volatile, the precursor, it still needs to be soluble in organic solvents that you put in a pot. Upon deposition, you need volatile byproducts, and you want, of course, for it to decompose into the material that you want. So this effectively boils down to kind of organometallic chemistry. So you'd be looking at a situation where you've got the metal that you're concerned with a pre-existing bond, the chalcogen that you're concerned with. In this case, I'm looking at sulfides. And then the rest of the material, the chemical, is an organic kind of backbone that is going to be lost to the gas phase quite easily upon decomposition. So thioureae, xanthates, and dithiocarbamates have been reported in the literature quite a lot. As you can see, they've got very similar sort of structures, but we're still not in a situation where we've got a precursor that's got a nice clean deposition, like decomposition, and therefore nice deposition. And these sort of materials, it's not easy for you to broaden them out to the selenium and tellurium atoms. So my project aim was to design and synthesize a series of novel zinc chalcogenide precursors for aerosol cystic chemical deposition. So with what we already knew, I designed this precursor. So it's thioanidase, so in this case, zinc thioanidase. So quite similar in the fact we've got a metal center with a pre-existing bond to a chalcogen, and then a slightly different organic backbone, which I thought would decompose slightly cleaner. In order to play around with the sterics and the electronics of this system, I wanted to try some slightly different R groups here. So I've got isopropyl, T-butyl, phenyl and cyclohexyl. This was so that I can both make something that was stable, but also I knew would be able to decompose. So that's what I did. Came to the synthesis. All of this was done air sensitively, so it took 10 times longer. But really quite nice actually. So kind of 2 chemical, 1 hot to make my organic ligand, characterized by NMR, and it's got some reasonable yields as well, which is nice. Then stuck that onto zinc. So used a quite standard zinc starting material, reacted it with 2 equivalents of my ligand, and in all 4 cases, I was managed to successfully synthesize these zinc thioamidates. I got some moderate yields, and we're characterizing by NMR and X-ray crystallography, but I won't go into the detail of that today. So it's all well and good making 4 compounds. I wanted to make sure that they were viable precursors for aerosol chemical vapor deposition. In order to do that, I needed to make sure that, first of all, that they would decompose into the desired product, i.e. zinc sulfide. Easiest way to do that was to do some thermometric analysis. Very simple technique. All you do is measure the change in percentage mass with an increase in temperature of a sample, and this is all done in inert conditions. So what I'm hoping to see is the mass of my precursor break down into what would equate to a residual mass equivalent to zinc sulfide. So precursor into zinc sulfide. As a general, they all worked out pretty well. The only one that was noteworthy was this purple line. I think we can see it, which actually falls below the target line that I'm aiming for, which is better summarized in this table. So the observed residual mass was below that of the expected mass, which showed that there was some sort of volatile character. It's not the end of the world, but it wasn't quite ideal for me. However, the other 3 cases, I had a reasonable agreement between the expected and the observed, which indicated the formation of zinc sulfide. This is all well and good, but I wanted to have a little bit look a bit deeper into this, and so I suggested a decomposition pathway. You know, the decomposition pathway, you can have a play with what you're working with if you understand it better. And so this would start off with a beta hydrogen reaction, which allows you to boot off this alkene. The loss of the ligand in the second step, and you can't see it, but then this fragment would then break down into zinc sulfide and a nitrile here. Can I move them? Oh, there you go. And what was really nice about this was that when I looked at my tertiary butyl system, looking at the TGA of it, there's this initial thermal event which goes down to a mass, which corresponds really nicely with this fragment, which you can see is in this mechanism. So the first thermal event is called the decomposition pathway. This can also be said for the phenyl and cyclohexyl systems as well. So you've got these little shoulder kind of peaks, which correspond quite nicely to this fragment. It was also worth noting that the T-butyl system decomposed at a lower temperature. And my theory on this was that this first step of decomposition, where you're reacting with this beta hydrogen and beta hydride, on a T-butyl group, you have 9 hydrogens from which to choose from. Whereas when you've got a phenyl system, you've got 2, and a cyclohexyl, you've got 4. So the availability of that beta hydride allowed for a cleaner decomposition, which is really, really nice. In order to kind of take this a little bit further, I did some another study where I simply took this precursor, heated it up, caught what volatiles were booted off, and did an NMR of the residue and the volatile components. So it was really nice, as I had a residue which corresponded perfectly with the ligand that gets booted off, and volatile components that correspond to the alkene and the nitrile, which I was really happy with. So it basically put me in a situation where I had designed and synthesized a novel system and been able to characterize its decomposition pathway really nicely. And that fed into some of the research that I'm doing now. So this work aimed to investigate zinc thioamidates as potential precursors for aerosol-assisted chemical vapor deposition. I managed to successfully synthesize 4 of these that I designed, and doing some thorough analysis and some decomposition studies, found 3 promising designs, one of which had a really nice clean deposition decomposition because of the availability of beta hydride of the tertiary butyl group. So bringing this forward, next steps, deposition trials. I'm in a very one-sided arm wrestle with my deposition rig at the minute, where I'm trying to get this system deposited onto substrate. But then from then, I want to look at alternative metal centers. So I've started looking at titanium, hafnium, and zirconium, as these are materials that are metal bicarbonate. I've actually got an example of, I think this is a TGA of one of my zirconium systems, which shows a really nice decomposition. And then beyond that, I want to go further than the sulfides. I want to look at the selenides and the tellurides, the really smelly ones, and have a crack with similar systems, but with those elements which are also quite interesting. And that's me. I'd like to acknowledge Lieutenant Robson for his help, the support from the CDC and QSRC funding. And thank you for listening.
Thanks very much, Ted. I'm kind of making sure some of that helped one, but hopefully quite briefly working now. Do we have any questions for Ted? It's a question online. Yeah, this. We can't chat. Oh.
Testing. Can you hear me all right?
It's raised a hand.
Oh, it's raised a hand.
Yeah.
Okay, if you raise a hand, could you just turn your microphone on and just ask the question?
Is my audio coming through?
Yes.
Yeah.
Okay, cool. Yeah, cheers, Ted. I understand that because I've missed the beginning part. I understand if you do gravimetric measurements with a filter, you can get really different results if the filter has static charge on it. But I didn't catch if you used one or not.
Oh, I see. Okay, so sorry, I'm kind of talking to the ceiling. When I'm looking at the gravimetric data, all I'm looking at is to see whether, I don't know if you can still see the screen.
Yeah.
Yeah, it's coming.
Basically, if you can see at 100% mass, that's my precursor, and I just want to see whether it will decompose to give a mass that's associated with zinc sulfide. Does that make sense?
Yeah,
so
okay.
at this point, there is no aerosol plume. I'm not concerned with the formulation of the aerosol. This is purely the material within the aerosol.
Okay, cool, got it. Thanks.
Does that make sense?
Yeah.
Thanks, mate.
Any questions from online or in the room? So I'm back. Sorry, there's another one, Michael, online. Michael.
Hey, Ted. Thank you very much for your nice talk. I just didn't quite catch that. So it looks like you've got 2 distinct decomposition points on your TGA. What did you mention was the second decomposition point, and how did that relate to your mechanism? It looks like your mass is predominantly coming off at particular temperatures, but not. You've got a small section that comes off on each sample, apart from the purple one. Is there a difference?
Yes. So that comes from the mechanism that I predict. If you can see on my graph now, just above 40% percentage mass,
yeah,
I've got a fragment that I'm predicting is corresponding to that mass,
okay,
which I've been seeing present in my decomposition pathway. Is that what you're asking?
It was actually the second peak. So you've got a distinct second hump in there, around about 200 degrees Celsius.
I see.
Your ZNS. Yeah.
Well, I think I'm hoping that it's simply the fact that you've got the formation of that fragment, and then that decomposes. If you look at the top right-hand corner, I've got the formation of a nitrile and a zinc sulfides left over, and I think it's just a booting off of that nitrile that's been given by that thermal event. Does that make sense?
Yeah, that makes sense. Yeah. Thank you very much. Thanks.
Thanks, Michael.
I had one quick question. So I know this was on the back, but in terms of the aerosol assisted part, so these components are going to be, these compounds are going to be formulated and delivered in the lot. So I guess you're looking at the decomposition of these parent compounds.
Yeah.
When you deliver them, they're present in a
They're in solution. So in all cases, and in those of the literature as well, you simply take the precursor design and just stick it into an organic solvent, and that's going to be anything generic, really. In my case, probably kind of toluene or something generic, hexanes. You do it in things like tetrahydrofuran as well, which is another common one. I personally avoid that because it's got oxygen in, and I'm trying to avoid the oxides. I just want the sulfides, the selenides, and the tellurides. But it's simply it's the main active ingredient, but I have to dissolve it first and then spray.
Thank you. Thanks, sir.
Thank you.
We're now going to move